Good morning, everyone, and welcome back. Uh, Today's discussion will be the latest 2023 Jan paper. I advise all of you to do this paper as a mock exam. I hope you have done it with timing. As you know, it's 1 hour 45 minutes paper. So let's begin the discussion with the section name CQs. In which species does the transition metal have the lowest oxidation number? If you analyze the lowest transition metal have the lowest oxidation number. Which one? The copper first one is +1. Hexacyanoferrate is +3. Let me write the values here. This is +1. This is +3. This is +2. And tetra. This is carbon monoxide, not cobalt, carbon monoxide. Now, carbon monoxide, this is a neutral species, carbon monoxide, right? Carbon monoxide is neutral because carbon monoxide doesn't have any charge. This is not cobalt, this carbon monoxide doesn't have any charge, right? And it's just a ligand. Full ligand has formed a dative bond with nickel. So this nickel here has no charge because if the nickel has a charge, this whole complex will have a charge. So nickel is 0 here. Right? Just nickel element has formed 4 covalent bonds with 4 carbon monoxide. So this is 0. So lowest is 0 out of all. The complex sign of chromium-3 has a formula given where X is the overall charge. What is the coordination number of chromium in this complex sign? The coordination number is number of coordination bonds, right? Coordination bonds, which is the dative bonds. The ethylene diamine En forms 2 dative bonds. So there are 2 En molecules, 2 times 2, 4, and there are 2 chlorines, right? So overall, how many coordination bonds? 1, 2, 3, 4, 5, 6, right? 6 altogether. Because 2 chlorines and En, this En molecule forms 2. So 2 times 2 is 4 and 2 chlorines. So overall is 6. And the overall charge of this complex, this is chromium 3+, and En has no charge. Chlorine is -2. So +3 and -2 will be +1. +3 and -2 will be +1. Which complex ion is colorless? Of course, it's a straightforward question. Aluminium has no color. It's not a transition element. But the copper, iron, nickel, they're all colored. So aluminium has no color. It's a straightforward question. Right, which metal hydroxide precipitate is soluble in both excess aqueous ammonia and sodium hydroxide? We know zinc. That's also a straightforward question. Zinc hydroxide is a white precipitate. When you add excess alkali, it dissolves both the alkalis, both NaOH and excess ammonia. The zinc 2 hydroxide precipitate will be soluble. The formula of hydrated copper 2 bromide is given. What is the percentage by mass of water of crystallization in this compound? So what you need to do is you find the molar mass of the whole complex, right? Then you have the molar mass of 4 water molecules. So 4 times 18 divided by the molar mass of the whole complex into 100%. So 4 by 18 divided by the whole molar mass into 100%. So 4 times 18 divided by the whole molar mass of copper 2 bromide into 100. I will get the answer as 24.4. Get the answer as 24.4. Clear? The diagram shows how the relative color intensity of aqueous solution containing 0.001 moles of chromium-3 ions varies with increasing amounts of cyanide ions. So this is the relative color intensity. Maximum goes up to the amount of ligand. If it's 6, the intensity of the color is maximum. The diagram shows how the relative color intensity of an aqueous solution containing 0.001 moles of chromium ions, chromium-3 ions, varies with increasing amounts of cyanide. So this is chromium-3 plus. This is 0.001 mole. As cyanide ions are added, how it increases. Chromium-3 ions of a complex chromium-3 ions form a complex with EDTA, ethylene dimethylacetic acid, with a greater relative color intensity than the complex ion formed with cyanide ions. Which diagram shows a change in relative color intensity when increasing amounts of EDTA are added to aqueous solution containing 0.001 moles of chromium. Right? So greater relative color intensity. Now this is amount of ligand. Now see, the diagram shows a relative color intensity of aqueous solution containing 0.001 moles of chromium-3 ions. This is the chromium-3 ions. Increasing amounts of cyanide. The amount of ligand in moles 0.006. Now see the difference. This ligand, if it is 0.006, maximum absorption is there, which means 1:6 ratio, right? Here is 1:6 ratio. That means there can be 6 cyanide ions around the chromium. There are 6 cyanide ions around the chromium. So this is 3 minus, 6 cyanide ions. 6 dative bonds can be formed. But we know, as for EDTA, only 1 EDTA can be formed with chromium, because EDTA cannot be greater. I mean, 6 dative bonds. And he says chromium-3 ions form a complex ion with EDTA with a greater relative color intensity than the complex with cyanide ions. Okay? Which diagram shows a change in relative color intensity when increasing amounts of EDTA are added to aqueous solution containing 0.001. So here, chromium and EDTA ratio will be 1:1. Chromium and EDTA ratio will be 1:1. That means when EDTA complex is 1.001 here, that will be the maximum intensity. So this B is wrong. B maximum intensity is 0.003. Even D is wrong. Maximum intensity is 0.003. It has to be 0.001. So it has to be either A or C. But the thing is, here it says EDT has a greater relative color intensity. So here you can notice with A, the intensity of the color is slightly below 6. It has to be above 6 because intensity of the color is greater with EDTA. So it has to be above 6. So the ratio is 1:1, so 0.001, and the color should be, intensity should be greater than 6. So answer is C. Persulfate ions react slowly with iodide ions at room temperature unless a catalyst of Fe2 plus or Fe3 plus is added to the reaction mixture. Which of these is most likely reason why this reaction is slow without the catalyst? Of course, any catalyst, the job of the catalyst is to provide the alternative route with lowered activation energy. So when you have no catalyst, the activation energy will be high. That's the only thing catalyst can do. The only way catalyst can influence the reaction is via the activation energy. The cell diagram for electrochemical cell is shown. What are the half equations for the reactions that occur in the half cells? Half equation in left hand half cell. See, this is left hand is where the oxidation takes place. This is left hand. Fa2 plus 2 should turn to 3 plus. So it has to be either A or B. Right hand Br2 should be reduced to Br minus. Br2 should be reduced to Br minus, right? So here the solution junction or the salt bridge is represented by two parallel lines, and what you write on the right side is a reduction on the right side, which is the cathode, red cat, and oxidation is the anode, right, on the left side. And you can notice the single line is shown for the electrode, right? If it's a electrode is platinum. Otherwise, you don't show that. If it's a metal with a metal line, you don't show that line. And see, this platinum electrode is shown after the reduction. Here, the platinum is shown before the oxidation. And remember, it's not about the platinum, it's about the phase boundary. This single line represents the phase boundary. Phase boundary meaning if the physical state is different. If the physical state is different to the physical state of the other species, you have to show as a single line. If the physical state is same, like aqueous, you put a comma, right? Put a comma, it's the same physical state. So this is not a line which is used to distinguish the electrode. No, this line, single line, is for the phase boundary. So if it is in between iron and iron 2 plus, still we have to have a line, single line, to show the phase boundary. And then double parallel line, I mean the two parallel lines, double line, is for the solution junction, which is also known as the what you call salt bridge. Okay. What's the maximum volume in cm cube of oxygen needed for the complete combustion of a mixture of 50 cm cube of propene and 50 cm cube of butane? Right, so we have to write the equations here. Complete combustion of propene, C3, H6, with oxygen, we get 3 carbon dioxide, 3 water, right? 6 hydrogen, 3 carbons. As for the oxygens, you have 6 plus 3, 9. So you have 9 over 2 oxygens here. This is for propene, right? So you have 50 of propene, 15 to 9 over 2. You can take the volume ratio as the, the molar ratio as the volume ratio. So 50 into 9 divided by 2, you'll get 225. So this is the 225 amount of oxygen reacting with propene. So butane, let's construct the balance equation for that. So 4 times 2, 8, 8 plus 4, 12, so it's 6 here. So 50 reacting with 300, right? So 300 is the amount of oxygen. So 300 plus 225 is 525. That's the total amount of oxygen which reacts. It's all over question. A sample of air contains 405 parts per million of carbon dioxide. What is the approximate volume in cm cube of carbon dioxide in 250 cm cube of? It is again AS question, but you know the ppm, parts per million equation, amount of solute over the solvent into 1 million, right? So 405 is the ppm value into 250 over 1 million is this. So 405 into 250 divided by 10 to the power 6. Get the answer as 0.1. Straightforward question again. This question is about infrared and proton NMR spectra of amino acid valine. Which of these wave numbers ranges would you not expect to have an absorption in the infrared spectrum of wavelength? So you have 3,500 to 3,300. What is that? This is the OH. OH as in as the NH. This is NH, yeah. OH is in this carboxylic OH is in this range. Close, this little below 3,000 is the carboxylic OH. About 3,000 is the free OH, close to 3,500. This is the carbonyl. Check the data, carbonyl. So this is not found here. Not expected. The CH is close to 2,900 in that range. Of course, this can be even a CH. Yeah, you can check the data. What are the expected splitting patterns in the high resolution proton NMR spectrum of a line for the proton shown in bold? Splitting pattern for the CH3. This CH3, both the CH3 gives only one peak. Adjacent carbon has one hydrogen. So N is 1, N plus 1 rule. N is 1, so 1 plus 1 is a doublet 2. And CH, adjacent, CH, which CH is this? On the CH2 attached CH, this CH. Adjacent carbon is this, right? Here's a good question. Adjacent carbon is this. Hydrogen attached carbons, adjacent carbons, sorry. Hydrogen attached carbons, adjacent carbons are these carbons. How many hydrogens are there in that? Not 6, 7 hydrogens. So 7 plus 1 is 8. So it will be octet. So don't forget you have to add these hydrogens. 3, 3, 6 plus 1, 7. So N number is 7. N number is 7. So 7 plus 1 is 8. 7 plus 1 is 8. Octet. Grignard reagents are used to increase the length of carbon chain in organic molecules. What type of reactions occur with a Grignard reagent? It's a nucleophilic addition reaction. It's not a substitution. You are adding the species. So it's nucleophilic addition reaction. Benzaldehyde reacts with Grignard reagent followed by hydrolysis to form 2-methyl 1 phenyl butane 1-ol. So what is the formula of the Grignard reagent? This part is from the Grignard reagent. So it's a 2 halogen should be in the second carbon, right? Yeah. This should be the Grignard reagent. Is the answer like this? Yeah, B. Aldehyde, you get a secondary alcohol. Okay. A student hydrolyze a section of a protein and then use a thin layer chromatography to analyze the amino acid produced. What is the best estimate for RF value of the amino acid label? Like, so how to find the RF? Then again, this is all level question. I don't know why so easy questions are there this time. So this is the halfway you have to calculate. When I calculate in the RF value, this halfway distance, right? So the distance traveled by this, which is X, if I say, distance traveled by the solvent front Y. So RF is X over Y. What is the answer? 0.6. A polyamide has a repeating unit given. Which are the monomers? Which of these monomers can form this polyamide? You need to have a dicarboxylic acid or a diacid chloride is also fine, and diamine. This is one of the monomers, and this is the other monomer. Right, diacid chloride, or you can even have a dicarboxylic acid or diacid chloride is also fine. Then again, a straightforward question. A reaction scheme for the preparation of azodine from phenylamine is shown. What are the reagents and conditions for step 1? This is diazotization reaction, NaNO2 HCl, 0 degrees to 5 degrees. NaNO2, sodium nitrite, HCl, 0 degrees to 5 degrees Celsius. And again, a straightforward question. Which reagent and condition are used for step 2? Step 2, we have to react with 2-naphthol. In alkaline conditions, 2-naphthol is this. 2-naphthol is not 1-naphthol. 2-naphthol here is this 2-naphthol. This is 1-naphthol. Right? You can clearly notice it is the second carbon. So it's 2-naphthol. Auto position, auto attack. Right? And it should be in NaOH. That's why we say alkaline condition. 2-naphthol should be in NaOH, the alkaline conditions. The organic compound 4-aminophenol can behave as an acid and base. What is formed when 4-aminophenol reacts with hydrochloric acid? Only the base part reacts. With hydrochloric acid, only the base part reacts. So what's the base part? This is NH2. So NH2 turns out to be NH3 plus. Clear? Any questions there? That's the discussion of the MCQs. All clear? So I advise strictly at the exam not to spend more than 20 minutes. Right? You have 20 to 25 minutes maximum. After 25th minute, you just move on to the section B. Otherwise, you'll not have enough time to manage. Usually, you have 20 MCQs. So 25 minutes should be the maximum amount you should spend. Section B. Organic compounds can be analyzed using combination of qualitative analysis and quantitative analysis, spectroscopic techniques. An organic compound contains carbon, hydrogen, and oxygen, has a molar mass 136. Complete combustion of 5.26 grams of A in dry oxygen, the absence of water, produces 15.3 carbon dioxide and 4.18 water. Show that the formula of A is C9H12O. Right? You must show all the. These similar questions we have calculated before, done before, right? So first of all, you have to find the mass of carbon. Mass of carbon in carbon dioxide. So you got carbon dioxide is CO2, so 12 over 44 into this 15.3. Because if I take 44 grams of carbon dioxide, that'll be 15.3 carbon. So if I take 44 grams of carbon dioxide, we'll have 12 grams of carbon. 12 grams of carbon. So this amount will have how much, right? So likewise, you can calculate the rest of it. Right. So same way, calculate the rest of it. So this is, once you know got the masses, you can work out the moles. Right. So here you got 0.34773, and then you can find the moles. 0.34773 divided by the molar mass of carbon, which is 12. So you can work out the moles of carbon, right? This is the moles. Yeah, this is the moles. I'm sorry. This is 4 point. What I wrote here was the mole. It gave me the moles. Okay. So this is 4.1727. So the moles is what I wrote before, 0.34773. So same way, we can find the mass of hydrogen. If you take 18 grams of water, there will be 2 grams of hydrogen. 18 grams of water will have 2 grams of hydrogen. So how much of water is there? 4.18, right? So 4.18 has how much? That is point. Yeah, that's the moles. No? So you've got the mass, and which is then you can find the moles. Okay, you get the mass point, and you find the moles, which is I write the moles here. Give me the moles answer. 0.4644. So then from the mass, you can find the oxygen afterwards, right? We had done this in the previous lesson as well. The same question, almost same question. You got the masses. Total mass is 5.26. So mass of oxygen, 5.26 is the total mass minus the two masses, which is 4.1727 plus 0.46444. That is the mass of the oxygen, or the hydrogen, and you can work out the mass of oxygen, and you can find the moles. Right, you can find the moles. So once you find the moles, you know the molar ratio you can take. So you get CHO. You can work out the molar ratio, and it's 9, 12, 1. Right. So the empirical formula and the molecular formula will be same in that case, because the question says C9H12O. So the molar mass is 136. So if you analyze the molar mass and the relative molecular mass and the empirical formula mass is the same, with the same answer. Right. So in this case, the empirical formula is the molecular formula. Compound A contains a benzene ring and one side chain. A is oxidized when heated with acidified potassium dichromate 6 to produce a compound B, which reacts with iodine and aqueous sodium hydroxide to give a pale yellow solid C. So this has a benzene ring. Now see what's the compound? C9H12O. That means it's alcohol, because alcohols can be oxidized with potassium dichromate. And this has to be a secondary alcohol, because secondary alcohol gives a ketone with methyl carbonate group, right? So we can directly draw benzene is C6H5. So you have C9, that means 3 more carbons. So 3 more carbons with the OH in the middle. You know why the OH in the middle? Because then when you oxidize this, you get B, which has the methyl carbonate group. Because iodoform, you get a positive result for the iodoform in the presence of methyl carbonate group. Right? It has to be a 2-ol then. Compound B reacts with iodine and aqueous sodium hydroxide to give a yellow precipitate, yellow solid C. The yellow solid C is iodoform, which is triiodomethane, which is CHI3, triiodomethane. When A reacts with concentrated phosphoric 5 acid, which is elimination reaction, mixture of 2 structural isomers, D and E, both of which decolorize bromine. That means a double bond is formed. Now the question is, how do you form the double bond? How the elimination takes place? Will the OH go with the corner hydrogen to give a 1-ene, or the OH will go with the left side? Which one? Left side, yes, because if you go with the right side carbon, then you will not get geometric isomers, right? Because there are 2 conditions. for the geometric cis trans isomerism. So this will show cis trans or EZ. But if you have the double bond like this will not be correct, because each carbon should be attached to different entities. Each carbon should be attached to different entities. So if you remove the OH with the left side, the right side carbon, you get a 1-ene. 1-ene is not correct, right? Because you will not have different groups. When you have 1-ene, you don't have different groups attached to a double bond carbon. A reacts with concentrated phosphoric acid, it forms a mixture of two structural isomers. D exists as geometric isomers, but not the E. That means the other one should be this. This should be your E. But it doesn't exist as geometric isomer. It's a structural. D and E are structural isomers. Both will decolorize bromine water, which means both have double bonds. And but the thing is, E does not show geometric isomers. Clear? Compound F is a structural isomer of A, which also has a benzene ring and one side chain. F is not oxidized. That means it is a tertiary alcohol. Let me draw a tertiary alcohol here. Tertiary alcohol. Okay, this cannot be oxidized. The C30 NMR spectrum of F has 6 peaks. Draw the structure of F. You already drew it. Justify your answer by labeling the 6 different carbon environments. You can label the 6 different carbon environments. Of course, you can't use 6 colors, right? You don't have colors now. What you're going to do is you can put numbers or letters like A, B, C, D, simple letters or numbers. Because since it's 6, I'm going to use numbers. Let's use numbers. If I'm to label this as 1, CH3 as 1. I put both the CH3 as 1 because it's same peak. 2, 3. So these are the same. 4, 5, 6. Right? Similar carbon, you get the same number. Or you can say A, B, C, D, E. Right? That's also correct. Yeah. Compound G is a structural isomer of A. Okay. Which also has a benzene ring and a side chain. Fine. The mass spectrum of G, that means it has to be not a secondary. Yeah, the OH has to be, now see, OH has to shift in a different position anyway. The mass spectrum of G has a peak mass to charge 107. It is a structure of G. Now, what is the molar mass of this whole compound? At the beginning of the question, it is mentioned as 136 grams per mole here. 136 grams per mole, right? So now you got the mass spectrum 107. So 136 minus 107 will be 29, right? 29. That means you have to remove 29 from this molecule. 29 is corresponding to, we know 15 corresponds to CH3, mass of charge 29 corresponds to C2H5. So C2H5 group to be removed from this. The side chain only has 3 carbons. That means the OH in the first carbon. This should be the structure. So remove the C2H5. So when this undergo fragmentation, this will be the mass to charge 107 and C2H5. Of course, it will not be detected because it's a radical in the when the fragmentation takes place. So you can write this as explanation. You can say mass to charge 107 is this species and the C2H5 group is removed. Right? This is a possibility. Because we know the difference 136 and 107 is 29. 29 is from the C2H5 group. Clear? Any questions there? Right. Vanadium forms composite oxidation states +2, +3, +4, and +5. State the oxidation number of vanadium in Na3VO4. That means it's VO4 3 minus. X minus 8 equals -3. X is +5. +5. In aqueous solution, vanadium 2 exists as hexaqua vanadium 2 plus, but vanadium 5 exists as tetra aqua VO2 plus. Explain why vanadium 5 does not exist as hexaqua vanadium 5. Why? Because the reason vanadium 2 plus can exist as hexaqua but not 5 plus. Now what happens? What's the difference between vanadium 2 plus and vanadium 5 plus? Vanadium 5 plus has a greater polarizing power, right? Because this is larger, +2. This is smaller, +5. When the polarizing power is greater, the only thing we can think of is that see, 2 water molecules are less here. The size is also small. The amount of water molecules which can surround the vanadium +5 will be less. And not only that, that is for the reason why it has 4 water, but you can see VO2, the 6 water, 2 water molecules has given off H plus ions. Right, see, it has formed from H2O. This turned to O2, that means hydrogens are given and only the oxygen is taken. But what has happened here is that because of the greater polarizing power of vanadium +5, it has polarized 2 water molecule out of 6. Right? That means it has taken H plus, has polarized, and removed H plus from water. It has polarized 2 water molecules. Right? And it has given H plus ions. So you have the first 3 marks given. You can also talk about the space, but more than that, if you talk about the space only, I'm not sure. I don't think you get all 3 marks, because if you talk about the space of 5 plus being a small, you're only addressing part of the question, because it's not about only 4H2O. If the question is V4H2O 5 plus, if it's just like this, the formula of the complex is just VH2O4. If it is like this, then we can simply talk about only the steric hindrance, meaning the size of the vanadium. But that's not the case here. Not only V having 4 water molecules, the V has turned to VO2. That means out of the 6 water molecules, 2 water molecules have only given the oxygen. It has removed the H plus of the two water molecules. Why? Because vanadium plus 5 has a very high polarizing, very strong polarizing power due to its smaller size and greater charge. So it has polarized two water molecules, resulting the water molecules to lose the H plus ions. Okay. So first mentioned, vanadium plus 5 has a greater polarizing power. Vanadium plus 5 has a greater polarizing power due to its smaller size and greater charge. Due to its smaller size and greater charge. This causes vanadium to polarize two water molecules. This causes vanadium to polarize two water molecules. Right? Causing them to deprotonate, causing water molecules to deprotonate H plus ions. Causing the water molecules to deprotonate H plus ions. So, potassium, vanadium, sulfur, hydrogen, oxygen. Calculate the empirical formula of this compound, hence write the overall formula showing the potassium, vanadium, 3 plus, and sulfate ions and water of crystallization. So what's the ratio here? You can divide the percentage by the molar mass, that will be the ratio. What is the ratio? 1 is to 1 is to 2 is to 24 is to 20. So now the question says you have to write in terms of, you can't just say KV S2H24O20, right? It says there are sulfates, that means potassium, vanadium, there are sulfates, and there is water of crystallization. Now let's say potassium, vanadium is 1, sulfur 2, right? So sulfate means I need to put 2 here because there are 2 sulfur. So there'll be 2 sulfates. So then how many oxygens are left? Already I have shown 8 out of 20. So 12 oxygens are left, so I can put 12 in front of water. Then the oxygens will be balanced, as well as the hydrogens, but there are 24 hydrogens. There are 24 hydrogens. Clear? An acidified aqueous solution of potassium manganate 7 oxidizes vanadium 3 ions. Yeah, vanadium 3 ions can be oxidized to vanadium 4, vanadium 5, maximum vanadium 5. In experiment, 10 cm³ portions of solutions containing 0.132 mole per decimeter cube vanadium 3 ions are titrated against 0.02 mole per decimeter cube potassium per manganate in acidic conditions. The mean titer is given. Okay. Calculate the ratio of the number of moles of manganate 7 to the number of moles of permanganate in this oxidation. What is this? This is just to find the molar ratio, right? That means you have to find the moles first. Moles of vanadium. N equals CV. Here the concentration is given, volume is given. Concentration is given, volume is given. So just apply N equals CV. And then moles of permanganate. This is how much? 26.40. N equals CV. 10 power minus 9. How much is that? 2 to 6 point. 10 power minus 4. So now you can divide by the smallest value, the smallest, get the ratio. 10 power minus 4. No? You get 1 is to 2.5. That means 2 is to 5. 2 is to 5. Write the equation for the reaction between manganate 7 and vanadium. So 2 is to 5. 2 is to 5. To balance it with respect to water, because you can check the data booklet for this. 2 is to 5. To balance H and O, you have to add water. Manganese. H plus and H2O should be added accordingly. You can construct the two half equations and then equalize the electrons and add. Equalize the electrons and add. Okay. Vanadium 5 ions in acidic solution may be reduced step by step through its oxidation states. Yeah. Compare and contrast the use of iron and tin in this reduction process. Include the equations and E cell values for any reactions that occur, because if the reduction occurs, we know the E cell value should be positive. Then you have to accordingly select whether iron 2 plus is good, or whether iron is good or the tin is good, because more E cell, more positive E cell is the indication of the feasible reaction. So the data from the tape, only these data should be used in your explanation. Vanadium is given, all the vanadium from +5 onwards. Yeah, vanadium +5 onwards. +5 to this is +4, right? And this +4 to +3, and +3 to +2. So serial reduction step by step. And for these reductions, it says reduction can be reduced step by step. So you have to use oxidizing agents. Now we have to now analyze one by one whether tin is used or iron is better by analyzing and writing the half fills. These are all should be written as reduction. The vanadium should be written as reductions. The iron and tin should be written as oxidation. So we have to now one by one write and see which is the best. Okay. So how do you answer on the how many points here? 6, no? Okay. So first of all, you start. The order is important here. You have to start from vanadium +5 and select which one is better. If it's both positive, you can mention both can be reduced, right? You can do that. And let's see. Yeah, you can use both iron and tin. If you use iron, reverse this, it will be plus 0.44. So plus 0.44, you add to 1.44 if you use iron. If you use tin, plus 0.14 and 1 is 0.14, plus 1.14. So you have to construct the reaction. I'm not going to do this. You have to simply say E cell for iron. If you use iron, is plus 1.44. That is 1 plus, this is reduction, this is oxidation. E cell is what? E cathode minus E anode. So reduction minus oxidation. Right? So minus minus turns out to be plus. Minus minus turns out to be plus. Right? So that's why it's plus 1.44. And then this is for iron. And for tin, E cell value is 1.14. You add the two. Okay. So the question arises, are we to write one or both? Right? Are we to stick to one or both? Let's say. Compare and contrast the use of iron and tin in this reduction process. Okay. You have to compare and contrast similarity differences. So you have to write that both iron and tin can be used here. You can't just select one because both can be used. Right? So can say both iron and tin can be used to reduce vanadium plus 5 to vanadium plus 4. Right? And that you have to now construct the two equations and calculate the E cell separately and show. So that itself carries 2 marks out of 4 because iron 2 marks, iron 1 mark and tin 1 mark. So 2 marks there. Okay. So to construct the equations, I'm not going to do that part. You can do it. And then check whether which one can reduce vanadium 4 plus to 3 plus. Then again both. See? Because in reverse is sign negative becomes positive, and two positive values positive, right? So you have to, now the third point, you have to say both iron and tin will reduce vanadium plus 4 to vanadium plus 3, right? Both can be. So you have to now calculate a new E cell value. Plus 0.78 for iron, tin E cell value plus 0.48, and you have to construct the two equations. So two equations. You notice this is the paper 5 is essay question is the most easiest out of, even more easy than the AS, right? Nothing much to write, mainly equations, right? So, but it should have a proper flow. The order is important. Systematic approach, right? So the next you can say both iron and tin can be used to reduce vanadium 4 plus to 3 plus, and you write the two equations and calculate the E cell values and show because the E cell is positive is feasible. So 4 marks so far. And then the last point is what is important. Reduction of vanadium 3 plus to 2 plus. Which one? Can we use both iron and tin? No, that's right. We can only use iron, not tin. Why? Because of the overall negative electrode potential with tin. That's the last 2 marks. So to say iron will reduce vanadium 3 plus to 2 plus, you can construct the overall equation, right? That is with this, and show the E theta cell value is plus 0.18 volts. right? And you construct the equation for that, which is vanadium 3 plus iron, vanadium 2 plus, Fa2 plus. And that is the fifth mark. And then finally you say the reduction of vanadium 3 plus or 2 plus cannot be achieved by tin, as the overall cell potential is negative. This reduction cannot be achieved by tin, as the overall cell potential is negative. Okay, clear? Any questions there? All clear up to this point? Okay. We'll take a short brain break of 5 minutes and we'll continue the rest of the discussion after the break. Right, let's continue. I hope everyone is back. This is question 19 of section B. This question is about some organic nitrogen compounds. Phenol reacts with dilute nitric acid at room temperature to form a mixture of 2-nitrophenol and 4-nitrophenol. This reaction is like electrophilic substitution. Draw mechanism for the reaction to form 2-nitrophenol. Assume that NO2 plus is the electrophile. That means how the electrophile is produced is not important to show here. So 2-nitrophenol. So this is phenol, the NO2 plus second group, second carbon it attacks to. So this is NO2 as a hydrogen adjacent to adjacent the positive charge, and then this breaks in the presence of the base, which is HSO4 minus, but we need not to show that. So this is how the two, this is same mechanism, but make sure that the horseshoe is open. The relocalization should be from the adjacent to adjacent. That's very important. We have found so many of this nature. You can show the base, which is hydrogen sulfate, or you can just simply say, of course, nitration of phenol, we don't need to add a catalyst, right? So here we don't need to show that point, or just put B and taking H plus, otherwise just breaking the CH bond towards the benzene ring is also fine. Benzene requires a mixture of concentrated nitric acid and sulfuric acid. Benzene requires, not phenol, right? At 60 degrees to form nitrobenzene. Explain why phenol requires milder conditions. You don't need to use the catalyst or warming such high temperature is not necessary, because phenol can be nitrated just by adding dilute nitric acid. And if you use conc nitric, you get 2,4,6 trinitrophenol, which is picric acid, which is a white precipitate. But if you use dilute, then you have 2-nitrophenol and the 4-nitrophenol separately. So that's okay, right? I mean, separately. Here we use dilute, that's how you get 2 and 4 separately. So why phenol requires milder conditions? We know the reason. The oxygen on the phenol, the lone pair of the oxygen atom, the phenol, increases the electron density, right? On the benzene ring. So electrophiles will find benzene more attractive. So the 2 lone pairs on the oxygen atom get delocalized with the pi system, enriching the pi electron cloud. So electrophile will find the phenol more attractive for the electrophilic attack. Device synthesis of N-phenyl ethyl ethanamide from bromomethylbenzene without the use of Grignard reagent, without the use of Grignard reagent. Include reagents, conditions. Yeah, because why they say without the use of Grignard reagent, otherwise you can do it in, I think the Grignard reagent, you can do it in less steps. Right, okay. So if you can't think forward, you can, the best thing is to go backwards, right? Even forward you can, but it's much easier to go from backwards. See, if you can make this NH2, this you react with the acid chloride, you get that, right? So now you have to only make this. How to make this? You can have a cyanide. When you have a cyanide, you can lithium, add lithium, aluminium hydride. We have done more advanced conversions than this, right? So this is nothing. If you can go to the last study pack we did, organic synthesis conversions, we had done about nearly more than 40 conversions. All the advanced ones are given, so this is nothing, right? Remember this reduction, we should not use hydrogen nickel catalyst. For this specific one, is better to use lithium aluminium hydride, not sodium borohydride. And we should also carry out acid hydrolysis here. Acid hydrolysis should be done. And then we know how to convert the haloalkane to cyanide, which is ethanolic KCN, heat under reflux. Ethanolic. So 1, 2, 3 steps. 3 steps, 3 marks, and conditions get 2 marks. This is what 1 mark for this condition, another mark for all these conditions, and the steps each product, and the steps the remaining. Phenylalanine is naturally occurring amino acid found in meat, milk, and eggs. It is used to form artificial sweetener known as aspartame. Phenylalanine is given, aspartame is given. What's the difference between the two molecules? Let's just analyze that. So it will be easy for our next part of the question. This is the phenylalanine. This part is this, right? It's amino acid. Okay, complete the structure of the zeta ion of this. So you have to basically, zeta ion is ion which has two oppositely charged charges. So you got the O minus, the proton is the H to the amine group, forming CH3 plus. So H plus goes and protonates to the NH2, where NH2 turns out to be NH3 plus. How's the structure of the dipeptide form from phenyl alanine? 2 of these. Dipeptide means one. To dipeptide is di means 2 amino acids. Okay, when you name peptides, remember dipeptide doesn't mean 2 peptide linkages. The dipeptide there means 2 amino acids. Dipeptide will only have 1 peptide linkage. Di means 2, but it has only 1 peptide linkage. So we can draw this way. You can amide linkage should be there, right? Yeah. So this is NH2 can be drawn as NH2. That is another bond here. So this is NH2, and you got the carboxylic with the other NH, right? So you got this 2 of that reacts together, 2 phenylalanine. So this is 1 of it, and the other one is it correct? Yes. 1, 2, 3. Yeah, that's the amide linkage in between. Molecular formula of aspartame. How many? We have to add all. There's CH2 group here. CH, carbon, CH3 here. C, CH, CH2, C. And this whole thing is C6H5. So how many carbons? 14. How many hydrogens? 18. How many nitrogens? How many hydrogen, oxygen? Hydrogen, have to be careful. We can easily miss the hydrogens. That's the most important part. So be careful of the hydrogens. Two chiral centers. This is chiral. That's all. It should be carbon attached to 4 different entities. Carbon attached to 4 different entities. Aspartame is hydrolyzed by hydrochloric acid in the stomach. So when you hydrolyze amide linkage, you get the original carboxylic acid, and the original amino acids you get. Got the structure of 3 organic products formed for the complete hydrolysis of aspartame. So you have to break from the amide linkage. See, this is one amide, an ester linkage. This is one amide linkage. Sorry, not that. This one. This is ester linkage. So we can draw this molecule here. NH2 carboxylic acid. And then this part CH3OH. And the other part carboxylic acid. Draw the same shape so it's easy for us to draw then. Just break the molecule into 3. Amide linkage and there's ester linkage also, which gives methanol. So acid hydrolysis always gives the original reactant. Okay. If it is alkali hydrolysis, still possible, but you'll get the carboxylic part turning into sodium salt of carboxyl. That's the difference between the acid and alkali hydrolysis. The alkali hydrolysis, you get sodium salt. A can of fizzy drink contains 53 milligrams of aspartame per 100 grams of drink. It's very dangerous. It's aspartame, you know. You have the zero sugar drinks, they are the worst. Better to have the normal drink if you're forced to drink, right? Aspartame is carcinogen, right? You will not get fat, you will not put calories on, and you know, but you will die. So better to be fat and live, right? Than eating. Because people now, it's very tricky marketing tricks. You know, they use 0 calories, 0 sugar. You should never ever drink those. These are worse than sugar drinks, right? Because cancer. No one talks about cancer. They talk about diabetes and obesity. You can live being obese. You can live with diabetes, but with cancer, right? See what a worse thing they have done. See, this, don't forget, phenyl. These are lessons for life. Because your old A levels will go off with next week. But these you have to remember. Retain your chemistry for your life. See, whenever you see phenyl group, check the ingredients. Phenyl group, no, it's a proven, 100% guaranteed carcinogen. No second talk about it, right? So why they don't ban it then? So they have again those marketing terms. They say permitted colors, permitted preservatives, permitted compounds. So they will now prove to you just having this drink once, you're not going to get cancer. Of course, it's a small quantity, but the problem is you're not going to have it once. You just have once, once in lifetime you have aspartame drink, nothing is going to happen. Body will fight that, and but you are going to have it now every week or once in 2 weeks. This aspartame drink for next 3 to 4 years or 1 year at least. That's enough, right? So aspartame, see the amount of milligrams per 100 cm cube of drink. So at least 200 ml drink, you have about 100 milligrams of aspartame. That's a very big amount. Anyway, calculate the number of molecules of aspartame in 330 cm cube of the drink. Give you an answer to a appropriate number of significant figures. The molar mass is given. Avogadro's constant is given. Then again, this is the O-level calculation. So I hope you can do this. So first you find the milligram amount. So if 100 cm cube contains 53 milligrams, 330 cm cube contains how much of milligram? 53 over 100 into 330. So 174.9 milligrams, which is, of course, we can't do the calculation of moles with milligrams. You have to convert that into grams, right? Divided by 1000. So you get 0.1749 grams. And then you find the moles. That is the mass. The molar mass is given, so it's easy. .949 10 to the power minus 4 moles, right? So the question is what? Calculate the number of molecules. You got the moles. How to convert the moles into molecules? Multiply by Avogadro's constant. That's the answer. What's the answer? 3.58 or 20 molecules. Let's see, imagine the amount of molecules. 10 to the power 20 molecules. Almost like 4 10 to the power 20 molecules. Okay. So that's the section B. Any questions there? All clear? Manganese and some of its compounds. Manganese is a 12th most abundant element in the Earth's crust, and it is an essential element for all living organisms. Manganese is a transition metal and can form compounds at the oxidation states from +2 to +7, although all these are stable and some readily undergo disproportionation. Some compounds and ions containing manganese are effective heterogeneous and homogeneous catalysts. Alkaline batteries have manganese fluoxide cathode and are used in digital cameras and toys. They have a voltage, similar voltage to traditional zinc carbon batteries, but have a higher energy density and last longer. Some of the properties of manganese and its compounds depend on the electronic configurations, complete electronic configuration of the manganese atom and the manganese 2 ion. Manganese is 4s2 3d5, right? 4s2 3d5, so 1, 2, 3, 4. 4s2 3d5, so 2 plus, you remove the outermost 2 electrons. The standard electrode potential for half cells involving oxidation states +2 and +3 and +2 for manganese and iron are shown. Manganese 3 plus and 2 plus, okay. Explain in terms of electronic configurations by electrode potential value for the manganese 2 plus 3 plus. Half cell is significantly higher than 2 plus 3 plus half cell. Let's say what's the 2 plus? This is manganese. Now manganese 2 plus is stable. No? See, manganese 2 plus is stable. Why? Half fill the orbital. Let's write for iron. Iron is after manganese 26. So iron is like this. If you take just iron, you have 4s2. This is iron. So iron 2 plus, if I am to write iron 2 plus, that will be this, unstable. But iron 3 plus is stable. Iron 3 plus is stable. Got to compare with the electronic. So iron 2 plus is unstable, iron 3 plus is stable. Manganese 2 plus is more stable than manganese 3 plus. Now see, like we compare the iron, look at manganese 3 plus. Manganese 3 plus is not a half filled. When an orbital is half filled, it's stable. It's not stable. There you see empty empty orbital is there. So the theory here is that when orbital is fully filled or half filled is stable. So half filled d orbitals are stable. So which are the half filled d orbitals here? Manganese 2 plus and Fe3 plus. So that's why, see, Fe3 plus to 2 plus is less positive because you are going from a 3 plus is what? Stable. Stable and 2 plus unstable. This is unstable. So stable to unstable is other way around is better, right? Unstable to stable. But here, manganese 3 plus. What is 3 plus? Unstable. This is unstable. 3 plus and manganese 2 plus is stable. See, conversion of unstable to stable is more feasible, more positive. Conversion of stable to unstable is less positive. That means it's not easy. Right? So electrode potential, if it's greater, means more positive means more feasible for reduction, right? So manganese 3 plus reducing to manganese 2 plus is more feasible, more positive because it's unstable to stable conversion. Got it? So you can say half-filled d orbitals are stable compared to, yeah, you can simply say half-filled d orbitals are stable. Then you can write the configurations for Fe2 plus and 3 plus. Write this. And then say Fe2 plus is less stable compared to Fe3 plus. Fe2 plus is less stable compared to Fe3 plus. As it has 6 electrons in its d orbital. Then you can talk about manganese. Manganese, you can write the configuration for manganese 3 plus, and 2 plus already were written. Manganese 3 plus is less stable compared to manganese 2 plus. Manganese 3 plus is less stable compared to manganese 2 plus due to its partially filled d orbital. And manganese 2 plus has a half filled d orbital, which is stable. And then you can further say unstable conversion of unstable manganese 3 plus to 2 plus is more feasible. Conversion of manganese 3 plus to 2 conversion of unstable manganese 3 plus to stable manganese 2 plus is more feasible. Than the conversion of stable iron 2 plus, than the conversion of stable iron 3 plus to unstable iron 2 plus. Therefore, E theta will be less positive. E theta is less positive. Manganese 4 oxide is oxidizing agent and a catalyst. Chlorine can be repaired in the laboratory by reacting manganese 4 oxide with concentrated hydrochloric acid. In terms of oxidation numbers, why is redox? Manganese is +4 oxidation state, here +2, +4 to +2 is reduction, and chlorine is -1 here. 0, -1 to 0 is increase in oxidation state oxidation. So this is why it's redox, because both reduction and oxidation takes place. Okay, so to show manganese is reduced from +4 to +2, chlorine is oxidized from -1 to 0 with the oxidation states. You have to prove it. Manganese 4 oxide catalyzes the decomposition of hydrogen peroxide. 100 cm³ of solution of hydrogen peroxide decomposed to produce 86.0 oxygen gas measured at room temperature and pressure. Calculate the concentration of hydrogen. First is find the moles of oxygen, and then you find the moles of hydrogen peroxide, and you find the concentration. Again, no level question, right? So first you find the moles of oxygen. That is, molar volume is given. So volume 86 over molar volume. 3.58 10 to the power -3 moles. Hope your paper also will be easy paper like this, right? Moles of hydrogen peroxide will be 2 times of this, because 1:2 molar ratio. Many O-level questions here, right? So what's the concentration? Number of moles in 1000. So this is the amount of moles in 100. So if this is the amount of moles in 100, number of moles in 1000 is the concentration. 7.1667 10 to the power -2 moles per decimeter cube. Potassium manganate 6 is a green solid. Manganese 7 is purple. In acidic solution, manganese 6 ions disproportionate to form manganese 7 and manganese 4 oxide. So ionic equation now here, you need to know disproportionation reactions. This is this in acidic solution to give purple permanganate. Manganate 4 oxide is manganese dioxide. How to balance this now? In acidic conditions, if you add H plus to one side, opposite side, you need to add water. Okay, that's how we balance in acidic conditions. So how to balance this? So for, yeah, 2. Okay, now it's balanced. Charges have to balance as well as the elements. Charges and the elements should be balanced. Clear? Manganate 7 ions react with ethane dioate ions in acidic solution. Ethane dioate is oxalate ions. 2 experiments were carried out. Experiment 1, aqueous potassium manganate 7 was added to a mixture of excess ethane dioic acid and sulfuric acid. The concentration of manganate 7 ions was determined as the reaction progress. Concentration decreases. Okay, concentration is decreasing with time, but experiment 2, same volumes of and concentrations of solutions as experiment 1 were used, but some solid manganese 2 sulfate was dissolved in ethane dioic acid and sulfuric acid mixture before adding the potassium permanganate. The graph of the concentration of manganate 7 ions against time are shown. Now, what is manganese 2 sulfate doing here? Manganese 2 sulfate. Let's see. Go back to the statement. Manganese 2 sulfate. Now we know this manganese 2 plus is the product here. Manganese 2 plus is the product, but here in this experiment 2, you are adding manganese 2 plus. And if you remember that this specific reaction is an autocatalytic reaction. Remember in the theory I explained about autocatalytic reactions, that is a reaction where product catalyzes the reaction. The reaction where product catalyzes the reaction is known as the autocatalytic reaction. So here the product is manganese 2 plus, colorless manganese 2 plus. That's the product. So as a reaction progresses, as a product is produced, what happens? It acting as a catalyst. It catalyzes the reaction. So in experiment 1, manganese 2 plus is produced, so that catalyzes the reaction. But in experiment 2, you are adding manganese 2 plus. When you're adding manganese 2 plus, that means you're adding the catalyst from the beginning itself. So in experiment 2, you can notice the drop in the concentration is much greater. The drop in the concentration is much greater in experiment 2. Why? Because catalyst is present. When the catalyst is present, the drop is much greater because the reaction is faster. But in experiment 1, the catalyst is there, but not initially catalyst is not there. Right? See, here in experiment 1, the drop here is greater. But halfway through the catalyst concentration increases. But initially, this is slow. Right? This is fast. But here from the beginning itself, its drop is greater, fast, because catalyst is there already. Here, the catalyst we are adding experiment 2, manganese 2 sulfate. Okay. That's the explanation. So this is like decrease in the concentration is less. The product Mn2 plus produced, I can say the product Mn2 plus produced is a catalyst for this reaction. In reaction 2, in experiment 2, In experiment 2, the catalyst is present from the beginning. In experiment 2, the catalyst is present from the beginning. So the drop in the concentration of permanganate is greater. Drop in the concentration of permanganate is greater. But in experiment 1, initially Mn2 plus is not produced enough. In experiment 1, initially the Mn2 plus concentration is low. So they are not adding now. Experiment 2, we are adding Mn2 plus. Experiment 1, we are not adding. So initially the concentration of Mn2 plus produced is low, therefore reaction is slow. Therefore reaction is slow. But with time, as more Mn2 plus is produced, with time as more Mn2 plus is produced, the reaction is speeded up. Therefore, the drop in the concentration of MnO4 minus, therefore the drop in the concentration of Mn2 plus minus is greater after a while. After a while. Methylbenzene is oxidized to benzoic acid by heating under reflux with an alkaline solution of potassium permanganate 7. In experiment, 1.73 grams of methylbenzene was mixed with 7 grams of potassium permanganate 7. Excess of potassium hydroxide solution. The overall reaction is given. Show that the potassium permanganate 7 is in excess. So first we can find the moles of both and see which is excess with the ratio. So moles of KMnO4 as molar mass. That's the first step. Moles of potassium permanganate. What's the mass? 7 grams. 7. Mole mass is already given, so that makes the question, the calculation easier, right? And then moles of C6H5CH3, methylbenzene. Mass is 1.73 over 92.01884. It is 0.4 moles. So the ratio is 2:1. So KMnO4 only, of course, 0.01 of methylbenzene will react with 0.02 of KMnO4. So KMnO4 is in excess. You can say KMnO4 is excess. As 0.01 of methylbenzene reacts only with 0.02 KMnO4. So KMnO4 is more than twice. More than twice. State how benzoate ion can be converted into benzoic acid. You can add any acid because sodium benzoate is a salt of a weak acid. Salt of weak acid is alkali. This is alkali. This is alkali. So you can add any acid, right? Any acid. HCl, nitric. You can add any acid to this. Any strong acid can be added for this. Not an alkali because this salt of a weak acid is alkali. We know salt of weak acid is alkali. So the alkali will react with acid. So when you add any strong acid, sulfuric, nitric, hydrochloric can be mentioned. But you have to specifically state the acid. But just writing as acid hydrolysis is not correct. Because not we don't need to add you need to carry out hydrolysis. Just any strong acid is sufficient to convert into benzoic acid. Because if you have excess water in hydrolysis, what happens? Benzoic acid again breaks down into benzoate ion and H plus. So we need to make sure the water is not in excess. Yeah. So that's why acid hydrolysis, we mainly have a lot of water there and less acid. So that's why acid hydrolysis in this case is not correct. Clear? Alkaline batteries consist of anode made of zinc alloy and cathode made of manganese 4 oxide electrolyte of aqueous potassium hydroxide. The overall equation for the cell is given. Feasible reaction, write the half equations of the reactions at the anode and the cathode. Cathode is reduction, anode is oxidation. So what is what is oxidized here? Zinc is oxidized, zinc to zinc 2 plus, and reduction +4. This is +3. This is reduction. The cathode you should write as reduction. 2MnO2 reduced to Mn2O3. Cathode. Anode zinc. Now we have to balance this. This is acidic or alkali condition. See, this is balancing in, but you can check the data booklet for this because balancing in alkali conditions we don't study, right? Should I check the data booklet? And do you have the values in the data booklet for this? Check the data. Have they given any? On the materials, my website, you got the recent papers and the new syllabus data booklet. Should be towards the end. Yeah, this is the data booklet here. Let's check whether you got the half equations. Otherwise, you have to balance in alkali media. This is towards the end, last page, page 10. Do you have manganese dioxide in alkali media given? No. You don't have it. Zinc? No, this conversion of zinc to zinc 2 plus is what is given. Yeah, so then we need to know that part. But what syllabus says only balancing in acidic media. But let's see how to do that question. Okay. Alkali media, right? Balancing alkali media. But make sure that your overall reaction should not have any acid or alkali. This should be the overall reaction. So look, let's take one at a time. So let's take the zinc oxide one. Zinc to zinc oxide. So this is alkali media. So we need to add OH minus here. Because it's alkali media. Why add OH minus on this side? Because there's oxygen on the other side. So I need to balance that. So to balance that OH minus on this side, you add water. How many water molecules? Just one water molecule is enough. But there are two hydrogens there. So I put 2 OH minus to balance the hydrogen and the oxygen. And I can add 2 electrons on this side. So this is the anode half equation. Remember, There are rules like balancing in acidic media. We know you add H plus to the side where there's oxygen, opposite side you add water. Then it is how you balance acidic. But alkali media balancing is not in the syllabus, but still you can do this because, when you have the half equation zinc to zinc oxide and you say balancing alkali media, you understand that the OH minus should come on this side, right? Because then only you can balance the oxygen. Opposite side, you add water. Understood? So in balancing acidic media, we add H plus to the side where there is oxygen. Opposite side, you add water. But here in balancing alkali media, likewise the opposite. You add OH minus to the side where there is no oxygen. Opposite side, you add water. Got it? Another one more thing is that, say, for example, if you are balancing anything in acidic media, say, permanganate to manganese, right? Then you add H plus to the side where there's oxygen, opposite side you add water, and then you balance that water, the oxygen at 4 water, 8 H plus, and then you look at the electrons on the right side 2 plus charge, left side 7 plus charge, you add 5 electrons to make it 2. This is acidic media. So same equation if you need to balance in alkali media, of course the products will differ. You add equal OH minus ions equal to H plus, both the sides, right? Equal to H plus, you add equal OH minus ions both the sides. So 8 H plus, 8 OH minus, you get 8 water, right? And then you got 4 water here, so 4 water and 8 water will make it 4 water on this side. You can bring the 4 water from the other side to this side, it will become 8 minus 4, 4. So in your balancing this in alkali media, this is how the equation will look. Mn2 plus and 8 OH minus. The products are having the OH minus in this case. So simply you add OH minus to the side where there's H plus. And on equal sides, actually, you add OH minus. So anyway, this is not a part of the syllabus, right? But yet we don't need to know this. But because the question says hydroxide, we know when you have a half equation zinc to oxide, is well understood. I can't add OH minus to this side, right? I need to add oxygen, OH minus to the reactant side, right? Because alkali media reactant, so you add OH minus here to balance this oxygen. And then you add water on the opposite side. That makes the 2 OH minus. Now everything is balanced. So to balance the charge, you add 2 electrons. And we know anode is reduction. That's why electron should be on this side. But if you add OH minus on the other side, you might think, why can't I add OH minus on this side? And then add water on this side to balance this, right? You might say this is also possible, right? Then let's see whether you can balance these 2 oxygens. What about this way? Then if you balance this way, you notice something? Electrons comes on the wrong side. This is reduction. Electrons have come on the wrong side, which is reduction. Electron should come on which side? On the product side, because it should be written as what? As oxidation. Clear? I hope it's clear. So that's how we know which side to add OH. Trial and error, right? This is what we will do here. So then this is a cathode reaction. Cathode reaction, electrons has to be on the electron should be on this side. I mean the reactant side, reduction. Now let's see how to balance this. Now in this case, the OH should come on the opposite side. Right? Why? Because when you add the 2 equation, the overall equation should be this. The OH minus should not be there. Then you add 2 electrons to balance the 2 minus charge, and to balance that OH minus, you add water on this side. So when you now, because always you add electrons to the opposite side of the OH minus, because OH minus itself is negative. So when you add these 2 half equations, you'll get this overall one. Okay. The standard electrode potential for zinc oxide half cell is minus 1.28. Calculate this. So this is the E cell equals E cathode minus E anode. E cell is 1.43. Cathode is where reduction takes place. We need to find that one. So I'll take this as X. Anode, we already know. Minus 1.28. So minus becomes plus. So X is what? 1.43 minus 1.58. Minus 1.28, sorry. So you get plus 0.15, right? Plus 1.15. That's a good question, the very last one. Okay. So we are done with the paper. Any questions? Any further clarifications? All clear? So this is our last paper 5 discussion, the latest 2023 Jan paper. Hope everything is clear. No questions? Fine. So we have done all the paper 5s from 2019 onwards, right? All the paper 5s were discussed from 19 onwards, yeah. And if you remember the recent paper 6 we didn't discuss, I think the October up to from 19 to 22 May paper 6 we discussed, but the October paper 6 and the Jan 2023 paper 6 I left it to discuss at last. So just before the exam we'll discuss that, right? We'll let you know the date, maybe just one lesson we might need next month, discuss that. So if there's no further questions, I will conclude the lesson with that, and wish you all the best for the exams.